So, hello everyone, welcome to our talk on how we achieve 2x efficiency improvement on Trino at Pinterest. My name is Carlos Benavides, and I am a software engineer in the Big Data Query Platform team at Pinterest. So, we'll begin this talk with a quick overview of Pinterest's scale and our current Trino setup at Pinterest. We'll then discuss about the optimizations we did, such as Graviton migration, data metadata format optimizations, utilizing Trino improvements from newer rebases or newer versions, our cluster consolidation, and future work we have planned at Pinterest for Trino. So let's begin with a quick overview of our scale and how we use Trino at Pinterest. So our business scale at Pinterest is that we have over 480 million monthly active users. We have over 1.5 billion spins saved weekly, and we have over 10 billion boards. Our data scale is that we have exabyte of data in S3, and we have over 400,000 Hive tables, all of which is the data, or all of which is served on AWS. So we have thousands of Trino monthly active users across the company, and we currently process over 3 million Trino queries a month. Currently, we're running on Trino version 409, and our supported connectors are Hive, Iceberg, which are the major connectors that we use at Pinterest, but we also have support for Thrift and MySQL connectors. Currently, our cluster setup is that we have 2 ad hoc clusters, one FCAC or fine-grained access control cluster, and one schedule cluster, which serves for scheduled reports. So the problem that we had at the start of 2022 was that we faced the following issues. The number of queries have been roughly doubling each year, and because of that, our amount of queries have been, our workload has been increasing from organic growth. The top data sets that were queried or used were not in efficient file or table formats. These data sets were typically in a non-columnar format, such as sequence file, text, or CSV. We have dedicated clusters serving interactive query workloads for restricted data sets. So we did not have a consolidation of which cluster is used, or we did not have one cluster to serve all authorization or restriction access. So in order to support increased workload whilst maintaining infrastructure costs, we needed a way to make the necessary optimizations to increase the more amounts of workload and from organic growth. So now we'll talk about our first optimization, migrating our Trino clusters to AWS Graviton instances. Originally, we're using AWS R5 instances for our Trino clusters back in early 2022. We looked into switching from this instance type to AWS Graviton instances, as AWS Graviton instances offers better price to performance ratio, and the newer generation instances offers more network bandwidth. So in order to get an idea of production workload performance, we benchmarked the performance of AWS instances. More specifically, we're benchmarking the R6G instance against our current instance, which was R5, as we mentioned before. So we bucketed queries by the CPU seconds and used them to sample queries from each bucket. So we created buckets from the 10 percentile CPU buckets all the way to the 90 percentiles CPU buckets. And for each bucket that we sampled, for each bucket we created, we sampled 100 queries in each bucket. Interestingly enough, for queries that were not as expensive, so queries that were from the 10th to 50th percentile, we observed a 4% regression using R6G instances compared to R5 instances. In the other case, though, however, the opposite effect happened for queries that were more expensive. So queries that were the 60th percentile to 90th percentile, we observed a CPU improvement of around 4 to 5%. So using R6G instances, it led us to believe using for inexpensive queries, we'll see a small regression. However, for more expensive queries or more CPU expensive queries, we'll see an improvement. Switching to this new instance type. We then did a quick throughput benchmark, and we wanted to see how long it will take to complete 450 queries with a concurrency factor of 40 queries. Using R5 to complete these 450 queries, it took 64 minutes. And the other, using R6G, however, it took 60 minutes to complete the queries. And so we saw a throughput improvement of around 6%. And the queries we used were the same queries we used for the benchmark, taking 25 of each bucket and running them twice. We then were confident in rolling this out to production. And here's our production result from before and after migrating one of our cluster. Here where we're using the schedule cluster. So before the migration, we were using R5 instances, and we observed that the cluster max CPU utilization was around 66% before the migration. After the migration, however, we observed that we have a 3% decrease in CPU or max CPU utilization after the R6G migration. So essentially, we were able to withstand more workload just by switching the instance type. So now we'll talk about the wins and learnings from this Graviton migration. The wins we gained from this migration or optimization was that we received infrastructure savings by switching to less expensive instances, and CPU or queries that are more expensive use less resources to compute. We did have a few learnings during this migration or rollout. During the benchmarking stage, we noticed that tables that were not able to be parallelized, such as tables that may have had like one or few files in them, we observed a regression using R6G instances. We also noticed that tables that, for some tables or some queries that, despite the R6G being more efficient, they might have resulted in an increase in wall time compared to using R5 or R6i, which is another instance type we're benchmarking. So in order to help with the latency regression that we're observing using R6G, we decided to make our cluster a mixed environment where we'll use a R5 or R6i instance for the coordinator and R6G instances for the workers. So the idea of using a mixed environment was that it will help the wall time for the queries that were experiencing regression and latency, but were actually more efficient in CPU. Another issue that we found was that during production rollouts, a codec library was not available using new instance and using R6G instance. So we had to make a manual code change to make the Trino high module to load this missing class. The last learning we had was that we didn't measure the impact from the increased network bandwidth that we gained from upgrading or changing instance type. So for the next time, we want to be able to understand how much gain or efficiency we get from upgrading our network bandwidth. So now we can move on to our next optimization, which is our second optimization, data and metadata format optimizations. So another opportunity for our infrastructure cost savings and compute efficiency opportunity was that we want to consolidate our file format and table format to be Parquet and Iceberg. We want to migrate top query non-columnar data sets such as sequence file, text, CSV to Parquet, and potentially Iceberg as well. We want to do this migration because we estimated CPU improvements of about 30% for jobs that read from non-columnar data sets. Once these top data sets or top non-columnar data sets were migrated to Parquet and or Iceberg, we'll then be able to leverage the Trino reader or Iceberg reader, which will be more CPU efficient, as oftentimes users do not always need to have to query the entire column or an entire data set from the column. Sorry. So in order for us to migrate a data set from one format to another, we needed to make all downstream jobs compatible with the new data sets, whether it be Parquet or Iceberg. So for downstream SQL jobs, we leverage an internal library called Auto Migration Service or System, AMS for short, which helped automatically validate the data output for downstream SQL jobs using the new data sets. This library also made the necessary query rewrites for queries that need a query adjustment to be able to use the new data sets. This will also help the queries. Rewrite the queries without needing a code change. For non-SQL jobs such as Spark or MapReduce jobs, we leverage another internal library called Table API. This library helped us migrate programmatic jobs or non-SQL jobs by updating job spec to process on tables, Hive or Iceberg tables instead of file paths. We had a lot of challenges from this migration and learnings from migrating a dataset format to another. The major challenges we faced were non-SQL jobs required a lot of manual work, such as manual code change and manual data validation in order for a job to be migrated. This is slow in dev velocity point of view, as a dataset could have many non-SQL jobs or many downstream non-SQL jobs that require manual efforts. Another issue or problem that we had was migration and optimization issues that we observed during the migration from a non-columnar to Parquet or Iceberg. So one of these issues were both SQL and non-SQL jobs that do use majority or all columns oftentimes observe the CPU regression using Parquet. Another issue was that moving the original dataset to another, we observed that some datasets may have experienced storage regression, so the storage size increased moving to Parquet compared to sequence file or text. So in order to resolve this, we decided to sort the Parquet datasets to sort it by a column type that had a few distinct values. This way, it'll increase the likelihood of run length encoding to reduce it'll help the likelihood of run length encoding to reduce values. And it also keep rows with similar repetition definition levels close to each other. Another issue we found was that we observed CPU regression where a Parquet column may have had deeply nested structs which were always null value. This was causing jobs to spend up to 50% CPU time just to read these always null columns. We collected some stats to determine which rows or which columns will always be null, and then we pruned those columns that were always null by stop writing the repetition definition level for these always null columns. The last challenge that we had from this dataset migration was that in order for us to save cost and storage, we had a much smaller retention period for the shadow dataset, or in this case would be Parquet, so that we could save infrastructure costs during the validation of downstream jobs. The wins from this dataset migration or optimization was that we migrated top non-columnar datasets to Parquet and or Iceberg. With optimizations from null pruning and sorting, Parquet and Iceberg datasets storage size may decrease up to 35%. from the original data size. SQL jobs that read from these migrated datasets on average observe 50% more CPU and latency efficiency. With these optimizations, we're able to save on infrastructure costs as well as less computational and storage resources. The learnings from this optimization is that non-SQL jobs took longer than the expected time or timeline to migrate, as these jobs required more manual or more time for manual migration and validation and time to make these optimizations. And as I mentioned before, both SQL and non-SQL jobs that use majority or all columns from a dataset tend to perform worse in Parquet. So onto our third optimization. So here we'll talk about our most recent Trino version upgrade rebase. We have spoken about migrating datasets from a non-columnar dataset to Parquet and/or Iceberg. However, after the second optimization was completed, we noticed that the Trino or current Trino version at the time, which was Trino version 371, the Parquet or Trino Parquet reader was not as CPU efficient as other readers. We noticed that the newer versions of Trino at the time addressed this issue, and we decided to rebase our Trino version to leverage the optimizations from upstream. We decided to rebase on Trino version 409 as we want to leverage the new optimized Trino dataset readers. We want to be able to be on JDK 17, and we wanted to, and it was one of the latest Trino versions at that time when we decided to rebase. So here we restate the issue where we see that the Trino ORC reader in Trino 371 was nearly 9x more efficient than the Trino Parquet reader. This is because the Trino Parquet reader was using inefficient and expensive API to read Parquet data. Here we'll talk about the results we observed in production after the rebase. So before we rebase, our scheduled cluster was hovering around 67% max CPU utilization. However, we decided to rebase, and during the rebase, we actually ran into an incident, which was related to a transitive dependency causing regression in the coordinator, which we'll get to a little bit, or we'll get to the next slide. So we had an incident after rebase and during rollouts, but after we resolved the issue, our scheduled cluster stabilized of around 49% after the rebase. And during this time, the bytes scanned before and after the rebase was similar, and the amount of queries were similar as well. So the wins from this rebase was that the cluster max CPU utilization decreased from using the new optimized Trino readers. So we saved on infrastructure cost savings because we require less instances, as the Trino Parquet readers are much more efficient now. The learnings we had from this rebase was that migrating to Trino version 409 resulted in an unstable coordinator. This was a transitive dependency from Jackson, where the upstream upgraded the Jackson dependency to 2.14. As a result, we had to revert the Jackson version back to 2.13, which then solved the regression we're seeing in our Trino coordinator. The other learning we had was that we created a testing framework which will help us validate future rebases, as during this rebase it was a lot of manual effort, and it took quite a bit of manual effort for us to validate and test. So now we'll have a way to test and validate for future rebases, which will help the velocity for future rebases. So now we'll talk about our last optimization, or fourth and last optimization, consolidating our clusters. So our previous Trino setup at Pinterest around the time of early 2022 was that we had 4 clusters, which had four cluster use cases. We had ad hoc, scheduled, PII, and FGAC, or fine-grained access control. The issue we had with this cluster setup was that our PII and FGAC clusters were serving a similar purpose. The purpose was that it was restricting users from accessing sensitive data, in which case both clusters were generally underutilized as specific, or not that many employees would or users will have this data access. So we started to shift away from the IAM role-based access control in favor of fine-grained access control, which will offer the ability of, instead of using IAM role for access levels, we'll use session tokens access control, which helps provide the finer grained access control, where we can then restrict access of certain data sets using the end user's authorization or access, instead of using the cluster's IAM role. With that in mind, we decided to merge our PII use case with our FGAC cluster use case, which will then raise the utilization of our FGAC cluster. To provide a quick overview of Trino FGAC, first, the user authenticates 2 ways. The first way will be using OAuth, which will be generally used for ad hoc, and the second way will be used by Spiffy ID, which will be used for scheduled Trino jobs. Once a user is authenticated, we then request a delegation token from our Kerberized high meta store. This delegation token is then forwarded to workers, and the workers check with its token service for a STS token, which then grants temporary access to the data requested. We have a previous presentation by Yihi talking more about Trino FGAC in detail if you'd like to learn more. But this will just be a quick overview. In order for us to complete this merging project, we needed to convert our PI cluster use case to shift away from IAM role to STS tokens. Our Trino PI client's authentication or access shifted from using the cluster level IAM access level to using a service count access for their use case, as we are shifting away from using IAM to fine-grained access control, which will then use a service count authorization instead of using the cluster's IAM access level. The last thing was from this merging was that we are additionally adding more environment information from the clients to the token service, which will help us identify who is requesting what data and from where. So the wins from this optimization is that we received infrastructure savings from duplicating our dedicated PI cluster. We moved that PI cluster workload to FGAC, so our FGAC cluster is now more utilized, as all the traffic from PI is now routed to FGAC cluster. This also helps us be one step closer into consolidating our clusters to all be FGAC compatible, which will be the end goal at Pinterest. The learnings from this consolidation is that we had a few client implementations from our users. We'll need to be aware of these clients when migrating or merging one cluster to another. We have clients use case where it uses shared environments. So we'll have an environment for both ad hoc and scheduled, running on the same environment. We want to shift away from this, as providing authentication may cause more challenges than needed. So as a result, we are moving away from having shared environments and having scheduled workloads have to be scheduled on Kubernetes. So now we could talk about our future work. What we have planned for the next optimizations is that we want to upgrade our AWS Graviton instances from R6G to R8G. We also want to test if we could use R8G instances for our coordinator instead of using R6i. We would like to upgrade our Trino version to a newer version and in the coming year as well. We want to make all of our clusters to be FCAC compatible. So we want to upgrade our FCAC. We want to upgrade our ad hoc cluster to be ad hoc and scheduled cluster to be FCAC. And then we want to deprecate the dedicated FCAC cluster we have currently. Lastly, we want to support Trino ETL using Airflow, which all of this future work is currently ongoing. So that is the end of this presentation. Thank you for listening. And if there's any questions, please ask.
Yeah, thank you, Carlos, for that fantastic talk. We had a couple questions in chat while you were discussing the act of sorting the data. A question from Varun about, do you do it at the right time, and how do you decide on which column to sort on? And then Manfred was asking why you sort in the first place. So if you could dive into that a little bit more, that would be helpful.
So the first thing was we're sorting in the right time. And yes, that is correct. We're writing in the right time. And we decided to sort on the column that has like the lowest amounts of distinct values. So in general, this will be like, say, an event type based on a data set. So if this has a column where has a few distinct values, we decided to sort on that column. And the reason why we want to sort in the first place was that so it could handle the situation where we were seeing storage size regression. This is mainly because run length encoding wasn't able to be as efficient, and therefore was resulting to a bigger storage size as a result compared to the original data set size.
Interesting. Looks like we also have a question from Leslie. What client app are you using for getting STS token credentials for each user with respect to FGAC?
I'm sorry, what was the first part?
What client app are you using for getting STS token credentials?
We are using an internal app for that.
That tracks.
So yeah. So for that, to be in more detail, we did have a deeper dive of fine-grained access control at Pinterest by Yihi, which was another engineer in our team. So I guess for that, we could direct that question to a different presentation or a previous presentation.
And then I think we have time for one more question from Vanitha, which is, do you plan to push the changes that you did for the integration with token service upstream? This is a question that you get asked when you're at Trino Summit is, are you going to make it open source?
As of right now, we don't have a plan to. Maybe when we have our systems more mature and more stabilized, we could then have the talk of uploading or having putting the changes upstream. But as of right now, I think it's too new, and our platform is too new, and we're still in the process of making changes. So right now there is no plans to